This is the first of our design lessons, and I'm going to teach you about design. I'm not teaching you how to CAD. CAD's going to be separate. Really teaching you the processes we go through, the thinking we do, and the information we need to have in order to design a robot. CAD is an essential tool. It's really important to learn CAD when you're going through to design a robot, but it's the same way of saying it's important to know how to use a shovel if you're digging holes. CAD is an important tool, but it's not the same as design, and so we're going to stick on the design side. This first lesson is going to be probably the most esoteric of them. It's really how do you start, how do you come up with your ideas, your strategy, what's the process we go through when we go through that, really that first few days of build season where we have a new game and holy Hannah, what are we going to do with this game? How do we turn this game into a robot?
Wait, Clem, can I turn the camera a little bit? You're
it's okay.
Tiny bit cut out.
You can turn it.
Okay.
The other lessons are going to be a bit more focused on things like, the robot structures, how do you pick motors, how do you design for pneumatics, how do you design a drivetrain, a chassis. But this one, like I said, this one is how do we start, and the starting is always a little bit fuzzier than everything else. So, we start at the beginning by understanding what's the problem, what do we need to solve. We get back here from kickoff, we've seen the kickoff video, someone's downloading the instructions so that we can go through the robot rules and the game rules. But we really need to start by articulating the problem that we need to solve. That's a general term, not just for an FRC design, but I think there's a... You should come in now. You're missing it. Come in, sit down.
We won't bite.
Well, hard.
Well, that's not what I'm afraid of.
Okay. We start by articulating what the problem is. A lot of that's going to be articulating what the game is. But when we want to start articulating what the problem is, keep the solutions out of it. You don't want to, you really don't want to jump to a solution when you're starting out in the design process. You want to focus on the problem. What problems do we need to solve? What challenges do we have? What do we have to do without worrying about how we're going to do it? So keep the solutions out of the problem statement, keep it focused on the problem, quantify the problem to the extent that you can. Easy to do with FRC because you have scoring rules. So one of the first things you should do is put together a spreadsheet so that you can do what ifs on scoring. If I climb, how many points is that going to score? How many points can an alliance score by doing this? If I shoot balls, how many points can I score and how many points can the alliance score? Go through scenarios, especially once you have a scoring model, you can start looking at scenarios. How can we score the highest points? What can we realistically do in a game? You can simulate the problem. Simulate the game. We often run student bot games where we set up a field out in the other area, and we will assign different attributes to students, robot attributes. You'll be a tank drive robot, and you'll be able to pick up gears off the floor and score them. You'll be a swerve robot. You can't pick up gears. You have to go to a human player station, but you can shoot balls. And we'll run people through this whole process with those attributes, and you get to see how the games play out. It gives you ideas on how the game is going to look in real life, and it also lets you see on the field where the choke points are. Put up obstacles like our airship on the FRC game. That's a big choke point. It really defines where you can travel on the field, where you can't. So start doing that. Identify the issues, know where the choke points are, where a robot's gonna run into each other, where are you gonna lose sight of your robot? So if you're the driver, well, I'm not gonna be able to see the robot when it's behind the airship. How am I gonna handle that? Identify those issues, those problems. And another thing for FRC, and something that we've gotten fairly good at, is understand how the game is going to be played and the important factors for winning, and not just really through the whole season. When we first go to a week 1 event and nobody knows what the hell they're doing, the important attributes for winning are going to be different than they are when you get to FRC Championships or IRI, where now you've got most of your teams weeded out. All the teams that don't know how to play, can't play, don't have a good robot, they're gone. And you've got a small fraction of teams left who all know how to play, who all have good robots, and who all have been doing it for a while, so now they're experienced. That's going to look really, really different than Hatboro Horsham in week 1. And understanding what are you going to need to win at Hatboro Horsham. What are you going to need to win on Einstein? They're going to be different, but you really want to have a plan so that you do well at both, and you have the things you need to win at both. And I can guarantee that those things are going to be different. We focused this year on shooting. We didn't execute as well as we should have, but we understood that shooting was going to be important for winning at the high level of competition. It absolutely was. That was an accurate prediction. We also predicted everyone needed to climb. Yes, absolutely. Everyone needed to run gears. Yes, absolutely. But in principle, you could have a pretty good robot that ran gears and climbed reliably without shooting. That would be okay. But a really good shooter ended up being really the special robot this year. The one that got picked first, or was the one doing the picking. Yes?
So how typical was it that compared to like past year's games, like going back to like a decade, where it was actually a very small fraction of teams that could do a task very well? Like, cause this year for shooting was either you did it really well or you basically didn't do it at all, because your time was better spent on gear.
So 2 years ago, it was landfill stackers. The really, really, really good landfill stackers were the hot property in any alliance selection. If they didn't come in the top 8, man, they were the first robots picked. Think of 1-8. Were you at IRI 2 years ago? No, okay. We were picked by 118. 118 was an awesome landfill stacker. It was a beautiful thing to watch them. They stacked from the landfill faster than we stacked from the human player station. But in that game, you needed 2 human player stackers and a landfill stacker. And if you didn't have that combination, you were sunk. You couldn't win. We understood that at the beginning. We still picked to do we thought we were going to have something that could stack from the landfill, but we really didn't. We had a really good human player stacker. One of the best. But if I had a choice between picking us and picking a really good landfill stacker, I'd pick the landfill stacker. Last year, a robot that could get through all the defenses, could shoot into the high goal and still go under the low bar. That was a pretty good robot. So, yeah, they're usually a combination of attributes that you can say, this is a winning combination. If you can do all these things well, that's gonna be a great robot. Now, you don't know if you can execute on that, but I think every year it's probably true that there are a combination of attributes that if you execute on those well, you will have a robot that will be a winner. So how do you picture the game? And what do you know is going to be, how do you know what's going to be critical? What's going to be those killer apps? One thing you can do is look at some past FRC games for similar situations. And an example of that is in 2013 with the Frisbee game. And I know that most of you, all of you would have to go back and look at video to see this. It actually was a pretty similar layout of the field. And when you looked at this year's game and the traffic and that year's game, you understood that the traffic flow between those 2 years is going to be just about the same thing. And it was. From a traffic flow standpoint, 2013, 2017, basically the same games. On the other hand, we look back at an old book on the 2006 game, and they had ball shooting in 2006. And we found a lot of hints on how some of the best robots, some of the best ball shooters set up their hoppers, set up their shooting mechanisms, and we were able to learn from that in terms of, how do we get this shooting under control? How do we do that? So the other point on that is that you may end up picking different aspects of different games. The 2013 game, from the standpoint of it teaches you a lot about what the traffic flow is going to be. And the 2006 game because, well, you're going to be shooting a bunch of balls, and how do you do that? I told you we already talked about setting up a field, doing student bot simulations. That can be helpful. It lets you see and videotape how the student robots are going to actually interact with each other, how they're going to work. It's a little dangerous because sometimes the student bots don't do logical things. Go figure. With the 2015 game, with the tote stacking, none of the students stacked totes. They took one tote at a time. If you did that, if you learned that that was the thing to do from that simulation, you would have learned the wrong thing. Look at the scoring model and analyze it. Understand what ways of scoring are, first, what are the big ones, the ones that give you lots of points, but what are capped? This year's game, the rotors were capped. You could score so many points running gears and getting those rotors running. When you got the 4 running, that was it. Running more gears didn't help you. You did not score 1 more point. Getting 3 robots up, essential, had to do it. Not getting 3 robots up usually means you lost. But that was it, it's capped. So let's say you're playing a really competitive match and you're gonna guess, everyone's gonna get 4 rotors, everyone's going to climb. How do you win? And that's why we said, well, we need to shoot. Because that's the only thing in this game that's not capped. That's the only thing where you can score extra points once you've done these 2. In the Frisbee game in 2013, that's what Einstein looked like, because the Frisbees were not reintroduced back in the game. Once they were scored, they're gone. So what would happen is that basically all the Frisbees on Einstein, they were gone before the end of the match. And we ended up being picked because we could do a 30-point climb with our robot. And that turned out to be important, because when you came to the end of the game, it was that end game that indicated whether we're going to win or not. So what's capped, what's not capped? The balls look like a soccer bet from the scoring standpoint. Jesus, three balls to score a point, whereas I can get a rotor running and it's 40 points. I can climb a rope and it's 50 points. Why would I score balls? Because it's not capped, because it lets you go above and beyond what those other scoring methods can do. When they're finished and they can't score anymore, you can score more balls. And really, what can set you apart on a competitive field? And by the way, with any of these things, execution's critical too. It's important to have a good plan, a good strategy. You need to know that you can execute on that too. Article, yes?
How risky is it to specialize? Like this year, for the teams that just focused on solely on the gear and didn't bother with ball training, but we're compared to
Certainly a good gear runner is going to be an attractive pick, but it's not going to be my first pick. And I say that and recognize that our Alliance captain did exactly that. They picked a really good gear runner. And then they picked another gear runner, us. I mean, we had a good alliance, but we didn't have a really good shooter in our alliance. Yes, Ian?
Depends on like the game, because in 2015, there were very, very few teams that were able to do the landfill and the human player station. So almost every team specialized, or at least do both well. And so every team was specialized in that game because of how it was built. But games like last year or this year, there's more. It's easier to.
Mercury specialized that year also, when they specialized on the wrong thing.
what are the specialized?
And they specialized on, they could put a can on top of a stack after the fact. Interesting approach, but in the end, nobody needed that, because the winning robots were the ones that could build a stack with a can on top and a noodle in that can and score that. And it had to be a stack of 6. Some people came with stacks of 5. Not good enough. In 2015, the stacking game was probably the one that was the most obvious, that there's really only a couple ways to play this game. You gotta build a stack of 6, you have to have a can on top, it has to have a noodle in it. And the only question is, do I do that from the loading station, human player station, or do I do it from the landfill? Yes, Ian?
Just for the sake of argument, sort of, the world champion that year was a 5-stack can. So what do you think is the design idea behind that?
How many stacks do we get?
Could they do more that way?
Maybe
But
consistently 5-stack. But I don't know for sure.
the problem there is, did they have really good can grabbers? Can burglars?
Yes.
Because that was the other thing, is getting control out of the cans. But I'd say it's a lot tougher to win that way, because you're giving up a lot of points with, in the end, and the high scoring games, those cans became the score limiters. and you're giving up a lot of points, giving up 6 points for each can, if you can't stack 6.
I was just gonna say the can grabbers too, they were the multiplier.
Yep.
What was the stack of that one? What was the stack with?
There was 2 points at the tote.
It was 2 points for tote, but having a can on top
Triple.
gave you basically triple the
A
score.
stat? What?
And the full noodle gave you an extra 6 points.
So why was Mercury, when they specialized in cans, just because there were so many robots that could
Because
do
they have to
both
ask
stat
them.
and?
Yeah, because they thought that by doing that, they could fill a need, that there'd be robots that could stack but couldn't put a can on top.
But that wasn't.
And so they were gonna fill that need, and it turned out that that really wasn't the need. By the time you got into a competitive game, you really eliminated the people that couldn't build a stack with a can on top.
1089, correct?
What's that?
Team Mercury, 1089, is that?
1089. Now, they got to Einstein, by the way, because they were, actually, they were dead last in our division, but they got picked, and they got to Einstein.
Well, Sam, that's where the can burgers came into a big thing, because that was a multiplier. Instead of putting a stack of 6 up and getting 12 points out, we were able to get, what, 36 points?
Right, so at the beginning of that game, the 2015 game, you had 3 cans on your side, you had 3 cans on the opposing side, and then 4 cans in the middle. And the first and second of the game really decided who would control those 4 cans in the middle, based on the can burglars. And it became really, to some extent, the winner was determined in the first second of the match, because you saw who got the cans.
So in 2013, Frisbees were limited. Was a Frisbee ground intake, was that critical to success?
It was good to have one robot on your alliance that could do that. There were really 3 strategies that year that were good strategies. One was to have a cross-court shooter that could just stay at the human player station and shoot and score across the whole court. That was a good strategy, but you missed some. Another good strategy, which was our strategy, was a shuttle robot. We would run back to human player station, get 4 Frisbees, run to our pyramid, we'd shoot our 4, we'd score them, and we just go back and forth. And then we'd climb at the end. The third strategy that worked well is to, yes, I could go back to the human player station, or I could pick up the Frisbees on the floor that my cross-court shooter somehow missed. And all 3 of those were good strategies. Our alliance on Einstein was 1 robot of each. Yes.
One of the things, when that game, okay, now I just drew a blank, I'm sitting here waiting. I forget, I just went blank.
Okay.
5 stacks, citrus.
But anyway, a lot of these ideas, when we were going through and discussing in that first day or two, what's the game going to be like? A lot of these things occurred to us, and we ended up developing our strategy based on the way we thought this would work.
What I was just thinking about was the hanging at the end. Is it better to go for a 10-point low hang, maybe make a couple more runs as sort of Frisbees, or is it better to go for a 30-point high climb? That was one of the things they had to figure out too. What did you want to do?
Yeah,
Which direction did you want to go as a team?
correct. And our 30-point hang didn't work very often, but it worked when it needed to. Talk a little bit about brainstorming. So we understand the game now. We've done our scenarios. We've done our student bot simulation. It's time to come up with ideas on how we could play this game, what we want to do. And really, when you go through brainstorming, the first time you go through, you're not trying to figure out how you're actually gonna do anything. You're figuring out what you're going to do. I want to shoot balls. I want to stack 5 totes and a can on top. I want to do it from the human player station. I want to do it from the landfill. You're dealing with watts. You're not thinking at that time, well, how am I going to stack these? How am I going to get the can on top? That's for later. The first thing you want to focus on is what to do, not how to do it. So phase 1 is really an idea dump. Get as many ideas out as you possibly can without critiquing them at this point. I don't want to hear when we're doing this idea dump that, hey, that's a stupid idea, it'll never work. That's for later. If it's really a stupid idea. But, by the way, some ideas that are a little bit out of the box can either be really good ideas, or at least they can lead to good ideas if you don't squash them early. There are formal ways of doing this. Sometimes, mostly we just have people shout out ideas and write them down or post up post-it notes. 635 brainwriting is a formal method to generate a large number of ideas quickly. You get teams of 6 people, you give them each a piece of paper. They have 5 minutes to write down 3 ideas. And then they shift their papers onto the person next to them. And you do it again. 5 minutes to write 3 more ideas. And you do that again until everyone's written on each paper. Generates a lot of ideas. And at this point, a lot of ideas is what you want. Because if you have a lot of ideas, some of those are going to be really good ideas. A lot of them won't. That's okay. Phase 2 of the brainstorming is sleep on it. Take a break. Best if you actually go home and maybe you read the rules, maybe you watch a movie, maybe you get some other ideas, write them down. Because the next day you come in and we're going to collect those additional ideas that occurred to you in the middle of watching Ben-Hur while eating popcorn, or however they occurred to you. But if you let you let the game percolate for a little while, give yourself a little more time to think about it, things will come up that hadn't occurred to you in the first session. We want to collect those, and then we move on to phase 4, which is really collate the ideas, bring the ideas that are similar together to group them, but then critique them and narrow down. I will guarantee that if you go through this process of first looking really wide and collating them and narrowing them down to what you think are the best few ideas, you'll end up with different ideas than if you just picked the first 3 or 4 that came up out of people's minds. It's a good way of getting high quality ideas at the end of this process. Important, effective brainstorming requires well-informed participants. Following the old garbage in, garbage out concept. If nobody knows anything, your ideas are going to reflect that. It's one of the reasons we're doing this. Any questions so far? We're at the point now where we basically set our strategy. We select and prioritize our goals. You have some goals that are going to be necessary. You don't even have to think about it. Climbing the rope this year was a goal like that. Do we have to debate climbing the rope? No, we just got to climb the rope. Do we have to debate running gears? No, we just got to do it. Shooting, that had to be debated because that was not something you had to do. That was discretionary. So, deferrable goals. Are there things I have to do or I want to do, but I don't have to do them now? This year, basically shooting was a deferred goal. We had a shooter on the robot. It didn't really shoot worth a damn when we were at West Town. It got better as time went on and we solved the problems. But we understood that shooting wasn't going to be important to winning West Town or losing West Town. It was going to become important in later, more competitive matches. When you set your goal, quantify. I'm going to run 5 gears per match. We're going to score 40 points with the shooter. You really want to set quantifiable goals where those goals are appropriate. And things like, we want our robot to be able to move at 16 feet per second, because if I don't move at 16 feet per second, I can't run 5 gears. Important on setting strategy is you need to decide that you're not going to do some things. And those are at least as important as the things you decide that you're going to do. Except for the very, very best teams, you cannot do everything you can possibly do well enough for it to matter. Understanding what you can afford not to do is really important. The fact that we didn't pick gears up off the floor, it would have been nice if we could, but you know what? I think we made a good decision on not doing that. In 2015, not going after the cooperation totes during the qualifying matches was a good decision. You can debate whether or not going for the low bar last year, 2015, was a good decision or not, but it was a decision we made. Ultimately, we stuck with that because you have to. Usually, you can't fix these things afterwards. Once you set your goals, start setting specifications on what the different systems in your robot need to do. So the 16 feet per second is a specification. It's not really a goal. It's saying, in order to meet my goal of running 5 gears in a match, I need a drivetrain that can move at least this fast. Those are specs. Those are going to ultimately drive your design and your prototyping, because you know what physical attributes, what physical targets you have to meet with all of your systems. How many balls do I need to shoot per second with my shooter? What kind of accuracy do I need? What kind of speed do I need in my drivetrain? How quickly do I need to climb that rope? Those are all specifications that you can quantify on your robot at this point. Also, attributes like reliability, that's something that can be a specification. We need the shooter to work, or let's say we need the climber to work at least 95% of the time. If we don't climb 95% of the time, then our robot seriously sucks. Serviceability, reliability, those are important attributes to set earlier and say, this is our target for these attributes. I need this thing always work. I need, if I'm going to shoot balls, I need to score at least 70% of them. You can also at this time start allocating mass and costs in the different things. I can afford this many pounds and this many dollars for a drivetrain. I can afford this many dollars towards a vision aiming system, because I know I need to buy stuff if I do that. And ultimately, you've got hard targets on what you can spend, how much your robot can weigh. If your robot weighs 121 pounds, you're not passing inspection. If you spent $4,002, you're not passing inspection. You need to stay within the limits that you have. Now you've got goals. You know what you want to do. You've got some specs on knowing how well those things need to perform. Now it's time to worry about, how am I gonna do this? How am I gonna get 16 feet per second on the drive train? How am I going to shoot 4 balls a second and score 70% of those? How am I going to run 5 cycles of gears per match? How am I going to climb this rope in 10 seconds or less? So the focus becomes how. Generally, you split into smaller teams because you're working on focused, specific solutions. And like skinning cats, there will be more than one way to accomplish each of these goals that you set. And you don't want to jump on a solution. You don't want to say, I know how to do this, it's this. You want to have a few different ways that you've looked at, and really that you can explore and then pick the best one, the approach that's going to do the best job. This is time to research how other teams have accomplished similar goals in the past. This is when we looked into this book and started seeing, how did teams in 2006 solve this ball shooting problem from a hopper? You can also research outside the boundaries of FIRST, because a lot of engineering takes place outside of FIRST too. And see how in real life problems like this are solved. You can follow the same brainstorming approach.
Do you have room in your car for IRS? Can I have, no, you're going. Okay, cool. Thanks.
Start by going wide, get a lot of ideas down, then critique them, narrow them down. You probably don't want to spend 2 days doing this like you did the first session where you go sleep on it, take a break, come back, finish, because now you're getting to the point where you want to really understand, how am I going to attack this, how am I going to decide what's the best way of doing this. You should end up with a short list of viable options. If you have 10 or 15 ways of doing something on your list, or you haven't narrowed it down enough, you're not going to be able to prototype and evaluate 10 or 15 different approaches. If you've only got one, you've probably cut down your list too quickly. But if you have 2 or 3 different approaches, that's about the right number. You need to identify your gaps. One is going to be a knowledge gap. That's going to be most of your gaps going to end up being knowledge gaps. Where you don't know whether this device is going to meet the needs of your requirements of performance, or where you can't design that device without doing some testing, or areas where you could just run it up against robot rules. Those are knowledge gaps. Those can be solved mostly by either reading the rules or what? Testing. Very good. Testing is a great way to bridge knowledge gaps. A performance gap is where you've got an approach and you know it doesn't meet the performance requirements that you've set for this, but maybe with some development it could. And finally, manufacturing gaps will be areas where the team doesn't have the capabilities to make something. I want to do a sheet metal chassis, but we don't know how to make a sheet metal chassis. There you find a way of fulfilling that manufacturing gap. Maybe find a sheet metal shop that can do that for you. or you have to say, no, we can't do that.
So these are all essentially about our limitations, right?
It's really understanding what you don't know that you need to know in order to build a successful robot. And once you understand what those gaps are, you have to do something about it. You have to close those gaps or abandon the approach. Or you could go ahead without closing the gap and just rely on dumb luck. But dumb luck is not a very good indicator for a good robot. So you can do calculations, you can do modeling. Engineering allows you to calculate a lot of things. You can do prototype testing, and that prototype testing could be iterative, like it was with the ball shooter and the hopper they did, where we tested a lot of different approaches, and once we got something that worked kind of sort of okay, we continued to improve it until it worked almost,
Decently.
what?
Decently.
Yeah, right now it's a decent shooter. It took us a while to get there. And a lot of it's because we've never built a shooter like this before. We've built things that climb, we've built things that take things from one place and let them go. But building a shooter that could shoot something like 4 balls a second with reasonable accuracy, no, we've never done anything close to that. And further research. But one way you need to either close your gaps so that you know how to design this so that you know it's going to work. Yes?
So if you're in the middle of the build season and you identify a gap that absolutely has to be closed, what, like, other than through modeling, prototyping, if this is something like if let's say this season we somehow didn't know how to climb and we had to do it, how would we approach that? From just purely just design.
Copy other teams.
Well, that's one way. That's actually a perfectly valid way of doing it. But like we did do with the climbing, we built a number of different prototypes and we tested them. And the first prototypes that we built were kind of crude and they were just proofs of concept. Putting basically a stick with a bunch of bolts sticking out onto a drill and bringing it near a rope with a loop is not very refined, but it's a proof of concept. Once you get that, then you can start, well, how do we test this better? What are the design criteria we need? What do we need to know to design a climber? Turned out that the climber wasn't hard to design once we had that basic concept. And then we switched anyway and used Velcro, but that worked quite well. The shooter's actually a better question because the shooter went through a lot of iterations, a lot of changes. Because getting the rate and the accuracy that we needed was a lot harder than we thought it would be. So that's what you see on that system, particularly an enormous evolution from build season through the end of build season, and then in each of our competitions, we generally came in with something that was better each time, a little bit more refined, a little bit more testing, and more capable. Our climber got better over time for the same reason. It got better, it got more reliable, it got faster because we were able to go from a design where we knew it was going to work every time, but gearing ratio was conservative because it had to work. Till the end, we refined it. We used a more aggressive gearing because we knew by that time that we could use a more aggressive gearing and it would still work. You continue to gain knowledge throughout the season, put that to use, make improvements. Because you can't play the same game at Hatboro and expect to do well at FRC Champs unless you get better, unless your robot improves and your skills improve as driver. You're now at the point where you can seriously start to design the robot. This is what you really need to go through to get to the point where the design process can be. I'm going to just add some constraints, because first gives us constraints. First one is robot and game rules must be followed. You can't have something on your robot that's against one of the rules. The robot's limited in mass. It's 120 pounds without batteries and bumpers. That has been the same since at least 2005. The cost of parts and materials are limited. You can spend up to $4,000 on parts for the robot, not including the stuff that's in the kit of parts. You can have up to $400 that you can spend per item. So if you have an item that's $450, you can't put that on the robot. Yes.
That $4,000, I'm believing, if I'm correct, is what's on the robot. Does not include prototyping parts or anything else.
That's correct.
It adds on to it.
That's correct, and it doesn't include things that were on the robot, and then you say, no, that doesn't work, take it off, put it in the back of the workshop. That doesn't count. It's the things that are actually on the robot. Less the things that are from the kit of parts. So the kit of parts, you get some motors, you get a controller, you get some other aspect. Those don't need to be on the list.
What was our cost of parts and materials this year?
What's that?
What was our total cost this year for our robot?
3,900 and something. So every time you go to a competition, you need to bring a bill of materials. That bill of materials has the cost of all of the stuff that's on your robot. And the robot inspector looks at that and makes sure that it's legal. So don't show up at a competition without a bill of materials, because you need to get inspected. Other constraints, perimeter rules. These change year to year, but there are always perimeter rules. Your robot needs to be no more than this size by this size. It can be this tall. It can expand this much during the match, or maybe it can only expand by that much during parts of the match. You need to read the perimeter rules because they're always changing. Bumper rules apply, and those change also. Bumper rules change every year. Most years you need to have bumpers. 2015 we didn't. But you need to read those, because you're in big trouble if you go to your first match and you have non-compliant bumpers. Motors and many of the electronic and control parts are prescribed by the robot rules. So I've got a list of motors I can pick from. I've got a list of motor controllers I can pick from. I have a robot control computer that I must use. I've got a router that I basically must use. There are things that they're in the robot rules. You're allowed to use these parts or pick one from this list, but if you pick something that's not on this list, you can't use it. Fabricated parts from previous years. We build these pivots every year. We make pivot parts. A lot of them remain the same year after year. We don't reuse them because we can't use fabricated parts. You can use stuff you buy over again. I can take a bearing, I can take a wheel, I can take a motor. If it's something that I could just buy, I can reuse that. But if it's something that we made, I can't reuse that. I still also need to put the original cost of that motor or bearings or whatever else that I've taken from the old robot. I can't ignore the cost of that when I put together my bill of materials. I need to put the original cost in. Important, designs and software cannot be reused unless published. If I design a swerve drive, for example, and that works just great, I can't use that again next year unless I have published those designs, which is why we publish our designs every year. Yes?
That includes stuff developed in the off-season, right?
Yes. If I design a shifting swerve, I need to publish that. If I do vision software for targeting and I want to use that again, or if I want to use that for the coming build season, I gotta publish it. Putting it on our website constitutes publishing. And I have to tell you, most of the people who look at our website are not from our team. There are practical constraints. Robot on a cart should fit through standard doors. If you forget that practical constraint, you'll be very sorry, because you'll be figuring out, how the hell am I going to get this robot through the door?
I've seen it.
I'd say the same, another one that's not on here is that the robot should be able to fit into the crate that we use to ship it off to World Championship, because you don't want to have to build a new crate just because your robot's different. You want to think about things like, how are you going to pick up the robot so that you can carry it onto the field safely? There need to be places that you can grab hold of it that are safe handholds and easy handholds. The roller should fit into the trailer without any significant disassembly, because you don't want to have to be taking your robot apart just because you need to throw it in the trailer and move it. And that's all I have. Any other questions? Otherwise, we're done. And this will be put up on the website. Is this useful information? Okay, well, we'll get to try this out at the next build season. But this is the first time that we've ever actually gone through this and explained the process. Otherwise, it's just been sort of like magic. Okay, thank you.
Yep.